Hello, this is the quiz to review. This quiz is going to cover week 4, lecture 3 through week 7. And those topics are momentum, rotational motion, torque, and rotational inertia. Here are problems for you to review. Not going to read through all of them. It's a lot, but you don't need to obviously go through every single problem. But if there are specific topics where you feel like you could use some extra practice, here are some ones you can turn to, including lecture examples. But the examples I'm gonna cover are from week 4 practice, question 6, from week 7 lecture 2 application, question 1, and from week 7 practice, question 4. And how this is going to work is I have these slides. I'm not going to spend much time on them. They're more for you to like look back on because I want to focus on these examples. So linear momentum is a vector and it's mass times velocity. Also, we know this relationship where it connects to Newton's second law. So the sum of forces or the net force is the change in momentum or the time derivative of momentum. Then there's impulse, which is equal to the change in momentum, or it's also equal to the time integral of the force, or also the average force times the time interval. And conservation of momentum says that when the net external force on the system is 0, the total momentum of the system is constant, so the final is equal to the initial. Then we have our linear and angular variables. So we have our tangential velocity and acceleration and how they're related to their angular components. And then we have the radial acceleration, which is just really the centripetal acceleration. And that is the angular velocity squared times the radius. These are just the equations for the average angular velocity and acceleration and the instantaneous angular velocity and acceleration. The kinematics equations for rotational motion, torque, and remember what's important for torque is how far from the pivot point the force is applied, and then how much of the force is perpendicular to that radial line from the pivot point. Then there's the right-hand rule for torque. Where your fingers point in the direction of that radial line toward where the force is applied. Your fingers curl in the direction of the force, and then your thumb points in the direction of the torque. Then there is the rotational inertia. So this is rotational inertia for a single particle. And that's just the mass times the radius squared, or the distance squared. And for multiple particles, you would just sum it up. And then parallel axis theorem is for a rotational axis that is parallel to an axis through the center of mass of the object. And so what you end up with is the rotational inertia through the center of mass added to the total mass times the distance between those two axes squared. Then we have our table of rotational inertia. Make sure you have this to refer to, or at the very least, like the kind of most common ones that we use, either way. And then finally, equilibrium, which is a combination of both when the net force equals 0 and the net torque equals 0, and it's just a way to give you additional equations to solve for forces or things like that. Okay, now we're going to move on to the examples. First up is this question from homework 4, where we have an object that strikes the plane at an angle of 42 degrees and then bounces back up at an angle of 42 degrees. And we want to know the magnitude and direction of the linear moment. So I'm gonna show you two ways to figure out the direction. Because first we're gonna do vector subtraction, and then we'll do that. So first though, let's just draw the vectors. So here is the initial, here is the final, and then this is theta for both of them. But I want you to note that this does not give you the change in momentum. You can't just say, oh, change in momentum. No, because of the equation for change in momentum is final minus initial. This would be adding the two momentums together. So instead, change in momentum is the final minus the initial. So we have to do vector subtraction. So we'll draw the final momentum first, PF, and then we'll draw negative the initial momentum. I'm trying to make that more of a straight line. There we go. Negative the initial, and then our change in momentum is straight up like that. But that's not the only way you can figure it out. So we'll also do unit vector notation. So let's see. I'm going to draw the x and y components on here. So for the initial momentum, the x component is cosine, pi cosine theta, and that's I hat. And then the y component is negative, it's going down. So we're going to say subtract p initial, and then that one is sine theta j hat. And then I'll also just write what the momentum itself is, like mass times velocity cosine theta I hat minus mass times velocity sine theta j hat. And then we'll do the same thing for the final. And this time, so the x component still points in the same direction, and then the y component is positive this time. So p final cosine theta I hat plus this time p final sine theta j hat, and then that is mv cosine theta I hat plus mv sine theta j hat. And now we're just gonna subtract those from each other because the change in momentum is the final minus the initial. So we'll just write that out. So we have final mv cosine of theta minus initial, which is mv cosine of theta I hat. And then we'll put a positive here or a plus sign here. And then the final momentum is mv sine theta, and then we subtract, but the initial momentum in y is negative, so it's minus a negative, so it's adding sine theta j hat. So the x component is 0 and the y component is not. The y component becomes 2mv sine theta j hat, and then we can plug in those numbers now. 2 times 4.88 kilograms times 31.4 meters per second sine of 42 degrees j hat. And this gives us 205 kilograms meters per second j hat change in momentum, or up, either way. But yeah, so that's how we do this one. There was some There's a variety of ways that people tried to do this one, but I wanted to clarify and show you the right method. Next up, we are going to be talking about this one from week 7, lecture 2 application. So for this one, we're asked for the rotational inertia of this system, which is 2 point masses on a long thin rod that's rotating about its center. So I want to just specify, first of all, that these are point masses, so we don't need to treat them as spheres. We're also not given their radius, so we can't really treat them as spheres. But if we had that information and we needed to treat them as spheres, we would also have to do a parallel axis theorem for them. But let me show you how we solved this one in the first place. So the total rotational inertia is just the rotational inertia of the rod plus the rotational inertia of mass 1 plus the rotational inertia of mass 2. And this is a long thin rod rotated about its center, so that's 1/12 ml squared. 1/12 ml squared. And then for mass 1, it is the distance of 1/2 L. So we have m1 L over 2 squared. And then mass 2 is m2. This one's L over 4 squared. So we get 1/12 ml squared plus 1/4 m1 L squared plus 1/16 m2 L squared. And then we can just plug in our numbers. So we'll do that. 1/12. 2 kilograms, 1 meter squared plus 1/4, 5 kilograms, 1 meter squared plus 1/16, 3 kilograms, 1 meter squared. So this gives us 1.6 kilogram meters squared for the total rotational inertia. And I briefly just want to mention, as I said, if these were spheres, it's spheres, the rotational inertia for M1 would then be rotational inertia of the center of mass times mh squared. So this would look like, let's see, it's a sphere rotated about, rotating about its center would be, it's 2/5. Let me check. Solid sphere. Oh yeah, it depends on if it's a solid sphere or not. So let's say it's a solid sphere. And then it's 2/5 m1 r squared, and that being the radius of it. And then m1 and h would be the L over 2 squared. So this is using parallel axis theorem instead of summing things up. But that's how it would work if they were spheres instead of point masses. Okay, next example. So this one comes from practice 7. So we have a 52.3 kilogram uniform square sign that is 1.93 meters on a side and is hung from a 2.88 meter rod of negligible mass. Negligible mass means we don't have to worry about the weight force of the rod itself. A cable is attached to the end of the rod and to a point on the wall 4.12 meters above the point where the rod is fixed to the wall. We want the tension in the cable and the horizontal and vertical components of the force exerted by the wall on the rod. So let's draw this. We're drawing, excuse me, the extended free body diagram. The picture is already right there for us. So we have the tension force on this end. And then the sign, you can kind of tell, is attached at 2 points. So what we're going to do is put the force of the sign at those 2 points. Force the sign. And then we'll say that the force of the sign is just equal to 1/2 the weight of the sign. And finally, we're just going to guess on, well, actually, no, we'll write it this way. There's going to be an X component of the wall force because it asks for both, and a Y one. And we're going to guess that the Y component is pointing up. But once we get to that part of the problem, it doesn't matter whether or not you pick up or down. If you pick down and it's actually up, you'll just get a negative result. Just like if you pick the directions of acceleration and they're wrong, you'll just get negative, and that tells you that you need to switch the direction. So this is the pivot. It's the point attached to the wall, and it also kind of looks like it says hinge actually in the picture. And then we have our distances. So this is the 2.88 meters. That's the length of the rod. And then this distance is 2.88 meters minus 1.93 meters, which is 0.95 meters. Okay, and one more thing we should do is we don't know this angle. So we should draw the triangle. Or actually, we can just do it on here. So we have this distance is 4.12 meters, and then this distance is 2.88 meters. And we want that angle, so we want to do tangent of theta equals 4.12 meters divided by 2.88 meters, or theta equals the inverse tangent of those 4.12 meters over 2.88 meters. And this gives us an angle of 55 degrees. Okay, now we can do our torque table. So we'll say force, radius or distance, theta, and then the sine of the torque. Okay, so let's see. We'll just go from left to right. So we have the Y component of the wall force, but that's at the pivot point, so it doesn't contribute. We also have the X component of the wall force, also at the pivot point, also doesn't contribute. Then we have this first force of the sign, so F sine equals 1/2 weight sine. And that one is at 0.95 meters. Angle is 90 degrees. We'll get to the sine of the torque in a second. We'll do those all at once. Then we have the second sine force, which is 1/2 the weight, and that one is at 2.88 meters, also 90 degrees. And then finally we have the tension, which is also at 2.88 meters, and its angle is 55 degrees. Now we'll figure out the direction, or no, so, well, yes, the sine of the torque, which is also the direction of the rotation. So again, we pinch where the pivot point is. I'll try and do this in a way that is clear to you also. So I'll pinch it over here, and the let's see, the first weight force, that's gonna try and cause clockwise rotation, so that's negative.
Same with the second weight force, but then the tension force is in the opposite direction, so that's going to be clockwise, so that's positive. So we have negative, negative, positive. And let's just write out the torque for each of these. And we'll say this is sine 1. And so that's 1/2 the weight of the sine times 0.95 meters, negative. And then sine 2, negative 1/2 weight of the sine times 2.88 meters. And then the tension, 2.88 meters, sine of 55 degrees. Almost ran out of room. And then we'll do our net torque equation. And this is in equilibrium. So the net torque is 0. So we say the tension component of the torque, 2.88 meters, sine of 55 degrees, minus 1/2 weight S, 0.95 meters, minus 1/2 weight S, 2.88 meters. Okay, and then we just want to solve for tension. So we'll add the 2 weight torques to the other side. So we have tension times 2.88 meters. Then sine 55 equals, I think unit, I like to factor things out. So I'm going to say 1/2 the weight of S is just these distances added together, or times these distances added together. And then we'll divide everything except for the tension on the other side. And then we have the equation for the tension. So 1/2 the weight of the sine times the 2 distances, these are both in meters, divided by 2.88 meters, sine of 55 degrees. So this gives us a tension of 423 newtons. So that is the tension. And then we want to find the horizontal and vertical components of the force of the wall. So I'm gonna copy this guy onto the next page because we don't have enough room. And apparently we took the whole question, but that's okay. Okay, so this time we're going to do the separate it from the question. Nope. We're doing force. So we can just leave this as is, but I'll also, just to kind of help us out or help direct us, draw the regular free body diagram instead of the extended free body diagram. So let's see. We have the X component of the wall force. We have the Y component of the wall force, Y. We have the tension force, which is at an angle theta, tension. And then we have the 2 forces of the sine, force, sine, force, sine. Cool. Yeah, and then we should also put in the X and Y components of the tension. X, P, Y. Okay, now we will do the net force. So sum of forces in X equals 0, and that is just the wall force in X minus the X component of the tension. And then in Y, 0 equals, let's see, the Y component of the wall plus the tension in Y, and then minus the 2 sine forces. So this X component one was really easy to solve, so we'll do that first. We'll just add the tension in an X to both sides, so we get the force the X component of the wall force is equal to the tension times, let's see, X component is cosine theta. So that is 423 newtons cosine of 55 degrees. And that gives us a force of 248 newtons. Okay, so that one is good, but then let's do the Y one. So we'll just move it down here and say 0 equals the Y component of the wall plus the Y component of the tension. And then I'm going to plug in what we have for these sine forces. So it's just minus 1/2 the weight of the sine minus 1/2 the weight of the sine. Those are going to combine into just the weight of the sine. So let's do that. Y plus Ty minus the weight of the sine. Okay, now we can add the weight of the sine to both sides and subtract the Y component of the tension to get the Y component of the wall force by itself. So we have the weight of the sine minus the tension in Y. And the weight of the sine is just the mass of the sine times G, and then the tension in Y is the tension sine theta. And we can plug this stuff in, so we end up with 52.3 kilograms times 9.8 meters per second squared minus 423 newtons sine of 55 degrees. And this gives us 166 newtons for the Y component of the force from the wall. So those are in X, it is 248 newtons. And in Y, it is 166 newtons. And again, you don't have to know the direction of the force in Y. Or X, honestly, but the X one you could figure out. But you don't have to know the direction of the force in Y. If we were wrong, we would just get negative 166, and that would tell us that it's actually down instead of up. But really quickly, how you know the direction of the X force is that there's only one force in the X direction, other than the wall force, and that is pointing to the left. So the wall force must point to the right. Otherwise, the net force wouldn't be 0. And then again, if you were asked for the total force from the wall instead of just the X and Y components, this question asks for just the X and Y components, you would just do each component squared, added together, and square rooted. But again, they didn't ask for that, so we don't need to do it. Okay. So those were the examples for the quiz review. I recommend you go back to that slide that has example problems to review. Yeah, have a great day.